Hi, this is lecture 5, video 3, and we were talking about the effective complexity for certain hypothesis sets, and we figured that 2 to the n will not be as useful to us as we would like it to be. And so let's understand growth functions, and let's again look at effective complexity for certain hypothesis sets to understand if it is 2 to the n or not, or can something be done about it, right? So let's begin with that. And the very first hypothesis set that we are looking at is this 2D perceptron, because this is like our favorite model, easiest to interpret. Let us look at this two-dimensional space, and then these 3 points, 1, 2, 3. As you can tell that I'm definitely making this data set up, but that is for a purpose, and we will look at it, what that is. Let's say these are like 3 points, and this is deliberately I'm drawing it on a line. Okay, so what we're trying to do here is to list all possible dichotomies that can be implemented by the hypothesis set, which is my perceptron, right? So if you remember, in a two-dimensional space, perceptron is nothing but a line, right? So what all dichotomies can be implemented? By dichotomies, what I mean is, what are the possible values that these could take, given that my problem is a binary problem such that each of these could be like a -1 or a +1, right? So what all possible values can these take, and that could be implemented by my perceptron? For example, if all these points are positive, right, they lie in like one category, I can definitely like draw a line somewhere here, or some like in any with any slope, I don't care, right? But basically what I'm trying to say is that this dichotomy plus 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 can be implemented by my perceptron. Okay, let's imagine if this is a minus, this is no more a plus. Let me just remove it. Yeah, okay, so yeah, let's assume this is a negative, this is a plus and a plus. So of course, like I can segregate these into a negative and positive regions by a perceptron, which is nothing but a single line. So the dichotomy that can again be implemented by my perceptron is minus, plus, plus, right? Similarly, I can do a minus, and again, if I create like a minus here, let's say this is a negative, and this lies in the positive region, I can have a perceptron like this that can categorize and implement the dichotomy. So that's essentially what we mean by implementing the dichotomy. If all three are negative, definitely I can draw like n number of lines here to segregate the region into plus and minus. Similar to that, I can also implement this dichotomy, and let me see, plus, plus, minus, yeah, like plus, plus, and this one is minus. Of course, I can do that. Okay, so what case are we missing here? By now you would have figured there is one conspicuous case that we are missing here. Let me draw this picture again. How about if I have like this as a negative, like x1 as a negative? Let me write here x1, x2, x3 so that we don't lose track of what's going on. And this one is a positive and this one is a negative, right? Now, think about it. Can a perceptron implement this dichotomy? Well, let's try. Can I have a straight line that kind of segregates the plus and the minus? Well, if I draw a line somewhere here with whatever slope, I don't care. But then this will not be correctly implemented, right? If I have a line here, then a point here will not be correctly implemented and so on. If I try and sort of get something like this, I don't know, if I get something like this, one of the points will not be classified correctly, right? So basically what I'm trying to say is that these two dichotomies, especially if this point is minus, plus, minus, or if this is like a plus, minus, plus, and for this data set, what I mean by that is for these 3 points in this like specific sort of alignment, right? These two I don't think can be implemented by a perceptron. Okay, so if we just like base our everything on these 3 points, let's say, yeah, let me first write that down. There are 2 dichotomies that cannot be implemented. But if you remember, for 3 points, right, we figured that for 3 points, there were 2 to the n possibilities. But for this particular arrangement of these 3 points, I've come down, and maybe I can write it, that the complexity of the perceptron for x1, x2, x3, which we can write like this, x1, x2, x3, has come down to 6. Okay, why was this analysis important? This analysis is important because the underlying point that I'm trying to make is that we cannot look at a set of hypotheses separately from the data that we are trying to implement, right? So whatever we are trying to do in a machine learning problem, we have to look at the hypotheses from the lens of the data that we are working with, which in this case, right? And if you think about like 3 points, for example, this was the case, right? If we had like the dichotomy, which is like shown here in this picture, if we had the dichotomy negative, positive, negative, this cannot be implemented by the perceptron in this particular arrangement. Now, shown on the right-hand side here are 3 more points, right? And if we choose like a different set of 3 points, which is shown here in this picture here, any dichotomy can be implemented by the 2D perceptron model, right? If the data looked something like this, let's say this was my x1, this is my x2, and this is my x3, and if I had this one as negative, positive, negative, I can always implement a perceptron, right? So it kind of depends on how my data set looks like. And of course, for 3 points, I can clearly say that for 3 data points, right, the perceptron can, like, the maximum number of hypotheses that can be implemented on 3 points, right, is still 2 to the 8. Sorry, 2 to the 3, which is 8, sorry. Right? So you can see like all 8 are possible in this scenario here, but they're not possible in this scenario. Okay. So what does this tell us? First of all, there are ways where the maximum number of dichotomies that can be implemented depend on the data, of course. And going forward, we'll just see, can we do something about it? Does that like help us come down from 2 to the n to something better for certain problems, right? So that's why we are building on this. So what we can say here is that finally, the complexity m sub h of n for a perceptron with 3 points, like 3 data points in general, is 8, right? So that is exactly 2 to the n, hasn't solved a problem as much, but when my points were aligned something like this, it wasn't implementing all 2 to the n possibilities, right? So that's one point that I have, and I will be using that going forward. Okay, let's look at another example, which is slightly more complex than the one that we have looked at. So instead of 3 points, I'm looking at 4 points. And again, I had the liberty to choose the way they are sort of spread in my input space, and I did that. And again, my hypothesis set is my perceptron. Let me write it so that we remember. That's also important, right? So can all dichotomies, so in this case, there will be 2 to the 4 maximum. Can all of these be implemented with this data set, right? I am looking at this particular picture because remember when we were looking here, this was the alternating dichotomies, like the negative, positive, negative, or positive, negative, positive. They were the ones that were hard to implement for this particular case. So I thought of starting with the alternating ones, right? So I started with like this negative, right? Positive, and by the way, what I mean by that is this is x1, x2, x3, x4, right? So what I mean by that is this one takes negative, this one takes positive, then negative, and then positive. Okay, can we implement a perceptron that is going to correctly classify this? Can we think of a line like somewhere here? If I draw a line here, but this one will not be classified correctly. If I draw this, then this one is not correctly classified. So basically what's coming up here, whether I take this as negative, positive, negative, positive, or positive, negative, positive, negative, in either case, right, I cannot implement this under a perceptron, no matter how I arrange these points here. So for 4 points, right, 2 alternate ones cannot be implemented. And how many do I have? Like in total, I have 16. So I can directly go and tell for this case, of course, this is a simple case, but I can directly go in and check that these alternating cannot be implemented for 4 points, right? So that means that the maximum number of dichotomies that can be implemented by my perceptron on 4 points, which is denoted by, of course, the complexity as well, m sub h of n, is 14, because I'll take out these two, which are almost like completely impossible to be implemented, is strictly less than 2 to the n, which is my 16, right? So 14 is less than 16. And by the way, when we were discussing this earlier, we established that this is the maximum that my perceptron could have implemented, right? But in this particular scenario with 4 points, I can say that with just like 4 points, it's not really able to implement all of those 16 ones. In fact, two of them are pretty clear that they can never be implemented. So this gives us hope that the perceptron is not as complex as we thought, because we said like as with the error bar is going to become like really big, and the impact of n wouldn't be there, and all those issues were there when we were thinking that the worst case is going to be to the n. In fact, we were thinking that that worst case is going to occur every time we implement a hypothesis, which is not the case, right? So that's what we are, that's what gives us hope, right? Which means the moment we increased n, so we moved from 3 to 4 points here, right? And that revealed my increase in the number of points. It revealed a deficiency. I'd like to use that term because it revealed a deficiency that the effective complexity is not as bad, right? It's making the number of like the hypothesis that can actually be implemented, it's like making it deficient, right? And with an increase in like from 3 to 4 points, here we saw that, yeah, 2 to the n can be implemented with certain cases. But here, no matter what the arrangement of these 4 points is, you cannot implement it. And that is the whole point of the effective number of hypotheses. This kind of tells us that the effective number of hypotheses is, in most cases, not in all cases, in most cases, it is less than like this 2 to the n that we came up in the previous video. That's the first point. And the second point is, it depends on the hypotheses and my n, on how this deficiency plays and how much that deficiency plays. But that is going to be an important part of our analysis going further. The other thing is that this n, the value of n that creates this deficiency is important, right? So for example, in our perceptron case, this value equals 4 is important, because this is the point at which sort of like it broke the like the I would say the domination of like 2 to the n that we had, right? So it kind of tells us that at this point there is this evident deficiency. This is this evidence that, okay, I have this uncountably infinite hypothesis set, but not really, right? Because there are certain number of hypotheses in them that are not like implementable at all, right? So they're not as useful to us as we thought, and so we can just like discard them, which means that the number of hypotheses that can be implemented is definitely less than 2 to the n. And then obviously, as machine learning practitioners, it is going to be our sort of duty and our work to figure out what that n is for a given h. Okay, so what we're going to do next is we are going to look at a few examples and try to understand how this thing of deficiency plays out with different hypothesis sets and with different data sets. So that I'm going to cover in the next video.